In this problem, we're using an acoustic proximity sensor to measure the height of an object. We ran some tests to characterize the sensor's output voltage as a function of height and found that the sensor's output voltage, V sub s, is equal to 0.05 times the height in inches plus 0.2. We have a design requirement that the output voltage from the system should be 0.2 times the height of the object. So what we're doing here is changing the operating point so that the voltage is 0 when the height is 0, and also changing the sensitivity of the sensor so that it goes from 0.05 volts per inch to 0.2 volts per inch. We can use this circuit to accomplish the transformation. The sensor output voltage, V sub s, is applied to the circuit here. There are two parameters, R and VOFF, for offset voltage, that we can use to meet the design requirement. The output voltage from the circuit is governed by this equation. The solution approach is to substitute this expression in for V sub s here and find an expression for V out that's a function of h. Doing that gives us V out is equal to Vs, which is 0.05 h plus 0.2 times this expression here, 1 plus R over 10 kiloohms, minus V off times R over 10 kiloohms, this term here. Grouping terms, V out is equal to 0.05 times 1 plus R over 10 kiloohms times H plus 0.2 times 1 plus R over 10 kiloohms minus VOFF times R over 10 kiloohms. H is our independent variable. V out is our dependent variable. This expression here is the slope. And this expression here is the y-intercept. We can now equate these coefficients to the coefficients that we want for our desired output. Now let's do the arithmetic and solve for R and V offset. This is the expression we came up with for V out as a function of height. If we look at the terms that are multiplying H, this is the output from the sensor in the signal conditioning circuit. We want that to be 0.2. So equating the terms that multiply H, we get 0.2 is equal to 0.05 times 1 plus R over 10 kiloohms. Now equating the two y-intercepts, this is the y-intercept of the output from the amplifier, and the desired y-intercept is 0. Equating those two leads to 0 is equal to 0.2 times 1 plus R over 10 kiloohms minus the offset voltage times R over 10 kiloohms. From this, if we divide both sides by 0.05, we get 4 is equal to 1 plus R over 10 kiloohms, which means that R over 10 kiloohms has to be equal to 3, so R is equal to 30 kiloohms. Now that we know R, we can plug that into this expression here and here, and we get 0 is equal to 0.2. 30 kiloohms over 10 kiloohms is 3. 1 plus 3 is 4, minus V offset times 30 kiloohms over 10 kiloohms is 3. So VOFF is equal to 0.8 which is 0.2 times 4 over 3, or V offset, is approximately equal to 0.267 volts. So this should give us the performance that we need for our design requirements. Let's take a look at this same problem in a slightly different way, though, as a block diagram. Strictly mathematically, we've got this expression as the voltage out of the sensor. We're creating this circuit, so this is our transformation. This transformation is just linear. It's the same as the equation of a straight line. We have a slope times this voltage V sub s plus a y-intercept. And this is our required response. So the basic solution approach is the same. We take this, plug it in for V sub s here, and write V out is equal to M times Vs, which is 0.05 times H plus 0.2 plus B. We set that equal to 0.2H. M times 0.05 times H plus 0.2 M plus B is equal to 0.2H. So this coefficient here equals 0.2. The y-intercept is 0, so this is equal to 0. That means that I can write two equations to solve for M and B. So 0.05 times M is equal to 0.2. So M is equal to 4. And 0.2 M plus B is equal to 0. If M is equal to 4, B is equal to negative 0.8. Now we can look at the actual relationship implemented by the circuit itself. So V out is equal to M times V sub s plus B, where B is going to be negative VOFF times R over 10 kiloohms. From this expression up here, M is equal to 4, so 4 is equal to 1 plus R over 10 kiloohms, which gives R is equal to 30 kiloohms again. It's the same problem, so we should get the same answer. And minus 0.8 is equal to negative VOFF times R over 10 kiloohms. 30 kiloohms over 10 kiloohms is 3, so VOFF is equal to 0.8 over 3 volts, which is the same thing we got before. We're doing the same problem, we're doing it in basically the same way, we should get the same answer.